This is a continuation of our discussion under the dynamic characteristics of sensors. We already discussed the different dynamic characteristics. Now we discussed zero order systems, we discussed first order system, and now we are discussing the characteristic of a second order system. So we already derived the general form for a second order system. So this one is for a unit step or step input. So this will be the transfer function of the step input. So today we will be deriving the unit step response of a second order system. So unit step, our k will be equal to 1. So it's a unit step. So now our y in S domain now will be this one. Just copy this one. I'll just remove k here. It's just equal to 1. So we want to derive the unit step response. Unit step response of a second order system. So this is now our transfer function with a unit step. So in order to solve this, we need to go back to the time domain. So this is in S domain. So we need to convert this into a time domain function. So y's of t. How do we do that? We just use inverse Laplace transform. And how do we do inverse Laplace? So here, we have a quadratic at the denominator. So the method that we'll be using is through partial fractions. By partial fractions, we divide this into partial fraction. So I'll just copy this one. Then after that, we will be doing the inverse Laplace. So this will be case 1 of the partial fraction and also case 3 when the denominator contains a binomial and or a first order as equation and quadratic equation for case 3. So this can be divided into a over s, then plus for the third case b times s plus c all over the quadratic equation s squared plus 2 zeta gamma n s omega n plus omega n squared. So this is the partial fraction, and we need to solve for a, b, and c, the constants here. So there's two ways to solve that. You can substitute the value for s, making the other constant to be 0, or the other one is by equating the coefficients of the right side and the left side of the equation. So first, we can do the second method, but before that, we need to multiply both sides by this denominator. So we just need to multiply or cross multiply this. Copy. Or just cross multiply. So this will be omega n squared equals, so cross multiply, s will cancel out. So a times s squared plus 2 zeta omega n s plus omega n squared. Then here we have plus b s plus c, we multiply this with s. Then simplify this. You need to simplify this one. So omega n squared, we can distribute the constants. A s squared plus 2 zeta a omega n s plus a omega n squared plus bs squared plus c times s. We distribute them. Then we group all the s squared and all the s's and all the constants. So for s squared, we have a here and we have b, so plus b. So these are all s squared. And for the s, we have 2 zeta omega n a. Then we have plus c. So these are for the s. And the constant will be a omega n squared. Then we can now apply equating coefficients. So first, for coefficients that contains s squared. For the left side, we have no s squared, so it's 0. For the right side, we have a plus b. The next, the coefficients that contains s raised to 1. For the left side, there's no s. The right side, we have 2 zeta omega n a plus c. Then lastly, for the constant or s raised to 0, to the left side we have omega n squared, and to the right side we have a omega n squared. And from this we can derive now or calculate the values for a, b, and c. So we can use the last equation directly. We can solve for a. A here will be omega n squared divided by omega n squared, is just that equal to 1. Then we can use the first equation to solve for b. A plus b is equal to 0, a plus b is equal to 0, or this is just equal, your b is just equal to negative 1. Then for the second equation, we know a is 1, we can solve for c. So this will be 0 equals 2 zeta omega n times 1 plus c, or c will be equal to negative 2 zeta omega n. So we now solve the three constant a, b, and c. Then we can go back here. We can copy this and substitute the values for a, b, and c. And this will be our new transfer function here. So our a is 1, so this will be 1. Our b is negative, and our c is also negative. We can factor out that negative here. Then b is just negative 1, and c is 2 zeta omega n. And now this will be our new transfer function, and we can now apply, before we apply inverse Laplace, we can further simplify this so that we can take the inverse Laplace directly. So copy 1 over s. Here, we can apply completing the square at the denominator. So we have, this will be, so minus. Then here we have s squared plus 2 zeta omega n times s. Then we need to complete the square. So what do we add here so that this will become a perfect trinomial? So just take the coefficient of the second term, you divide it by 2, then you squared it. So plus, you squared it, 2 zeta omega n divided by 2 is just zeta omega n. Then we just square it, omega n squared. Then we add zeta squared omega n squared. So we need to subtract it again here so that we just add 0. So this will be zeta squared omega n squared. So we complete the square. Then at the numerator, s plus, I can divide this zeta omega n because I have here, the denominator, we have zeta omega n. So I can take here 1 of zeta omega n, then the other one here, zeta omega n. So if you add it, it's still equal to 2 zeta omega n. Why did I do that? Because if we divide these two terms now, we can divide this. So this will be 1 over s minus s plus zeta omega n divided by, we can now factor out the denominator, s squared, or s plus, because this is now a perfect trinomial. So this will be s plus zeta omega n squared. So this is the reason why I take 1 zeta omega n at the numerator, because I have s plus zeta omega n at the denominator. That will be my S. Then plus, we have here omega n squared minus zeta omega n squared. So we can factor out that omega n squared. Omega n squared. Then this will be 1 minus zeta squared. So that's the first one. And for the next one, we still need to add or minus, subtract zeta omega n all over the same denominator here. We have s plus zeta omega n squared plus omega n squared 1 minus zeta squared. But I need to put this omega n squared times 1 minus zeta squared at the numerator. So we need to multiply this by, I need to multiply this with omega n squared times 1 plus. So I already have omega n here, or just multiply this. Omega n squared multiplied by 1 plus zeta squared. We need to do this one so that we can use the formula or the table for the Laplace. It should be the same as this one. The numerator should be the same as this one. So we multiplied omega n squared plus times 1 minus zeta squared. So we need to divide it also here, somewhere here, so that we just multiplied it with, so I just put this one here. Omega n. So this will be also omega n squared 1 minus zeta squared. Then after that, we can cancel out the 1 omega n here. So we already have 1 at the denominator. So this will be, let's continue this. This will be equal to 1 over s minus zeta plus z, or s plus zeta omega. Just copy this one. Here. Then the last one, this will be minus. So we need, this will be zeta all over, we have only 1 omega n remaining. Then also 1 minus zeta squared. And then here at the numerator, we have omega n squared times 1 minus zeta squared divided by the denominator s plus zeta omega n squared plus omega n squared times 1 minus zeta squared. So now we can use the formula because this one is already the same as this. So the formula that we will be using is just direct from the table. That's just equal to sine. And this one, it's just equal to cosine. But remember, we have here s plus e. Remember s plus e? We need to multiply it by e. So now, our y's of t, applying inverse Laplace here, you're taking the inverse Laplace of this whole thing so that we can determine or calculate our time response. So we have here now in time domain, y's of t will be the inverse Laplace of 1 over s. The inverse Laplace of 1 over s is just equal to 1. Then minus, we have here s plus e, so this will be e. You need to multiply it by e raised to 80. This is positive, so it should be minus 80. Our a is zeta omega n. Zeta omega n t. Then the formula, of s over s squared plus omega squared. So that's just equal to cosine. Cosine of what? Cosine of this. Cosine of omega n squared, or square root of that. So this will be omega n, square root of omega n squared is omega n, then square root of 1 minus zeta squared times t. Then for the last one, so we can just copy this, zeta all over omega n times 1 minus zeta squared. Then you multiply it with this one, this will be omega over s squared omega. But we first need to multiply it by e, negative zeta omega n t. Then you multiply it with sine, the inverse Laplace of omega over s squared omega squared. Sine of omega n, the square root of this is square root of 1 minus zeta squared t. So this is now the final, we can still simplify this. And also we need to introduce another parameter here, the omega n times 1 plus zeta squared. Omega n times the square root of 1 minus zeta squared. This is actually called the damping frequency, or we just call it omega d. So this is the damping frequency, so that we can still simplify our equation. So here, so this will be omega d. This will be omega d. Then we have I can multiply omega n here. Oh wait, omega n. Wait, this should be omega n squared. Nope. Oh, wait. I have a correction here. This is the formula for this should just be omega over s squared plus omega squared for the sine. But I use omega n squared here at the numerator, so we need to remove that omega n squared, so we just need to multiply it with okay, so this should be omega n, or the square root of omega n squared times 1 minus zeta squared. So I need to remove this. This should be square root of 1 minus zeta squared, square root of 1 minus zeta squared. Why? Because our formula is omega over s squared plus omega squared. So the numerator is just omega, not omega squared. I did multiply it with squared and without square root, so meaning that's the square value. So in order to determine the omega, then just take the square root of omega n squared times 1 minus zeta squared. And that is omega n, the square root of 1 minus zeta squared. So this should be omega n. And this should be, we have here also, this should be omega n squared, because we multiply it with omega n and 1 minus zeta squared. So we only have here the omega n at the numerator. We cancel out the omega n here. So 1 minus zeta squared. So there should be this one. There's no omega n here. Should be the square root of 1 minus zeta squared. But we can put omega n at this part. I can multiply omega n at the numerator. Then I will also multiply omega n at the denominator. Why? Because this now will be omega d. This is omega d. This is omega d. So the final now of the time response, or the step response of a second order system, will be 1 minus, we can factor out that e minus zeta omega n t. Then you multiply it with cosine of omega d. We can now substitute omega d times t. Then plus zeta multiplied by omega n divided by omega d. Here, this is omega n divided by omega d. Then we factor out that e, then we multiply it with sine omega d t. So this will be our new time response, unit time response for a second order system. We will be using this to determine the different specifications of a second order system, the rise time, the peak time, the peak overshoot, and so on. But if you look at the damping frequency, now we have here a term square root of 1 minus zeta squared. So this is what happens if zeta is greater than 1. So if zeta is greater than 1, we call that the overdump. So it's possible that we have a greater than 1 value for zeta. So if it's greater than 1, and you square that and you subtract, then this will become imaginary. So therefore, this equation here is only applicable for underdamped system. Underdamped. What is underdamped? This is only applicable when zeta or the damping ratio is equal to or less than 1. So zeta here should be less than 1, not greater than 1. If it's greater than 1, then it's overdamped, it's not underdamped. So we cannot use this. So how about the overdump? How about if it's greater than 1? What will be the time response? So we can go back to our derivation here. And let's try, okay, here, I'll just copy this one. I'll just copy this one. It's still the same derivation from the beginning, but the only difference now is we can change this into a zeta squared minus 1 rather than a 1 minus zeta squared. So how do we do this? If you look at the last term, here, we did factor out omega n squared here, then it became 1 minus zeta squared. Now, what if I factor out negative omega n squared rather than positive omega n squared? So this will be 1 over s minus s squared, or s, just make it factor this out, plus zeta omega n. Then you square this. And here, instead of plus, just like before, we can factor out that minus omega n squared. So what will be the remaining term here? Omega n squared minus, so this will be zeta squared minus 1. So this will be zeta squared minus 1. So we did make it zeta squared minus 1. So here, if you substitute the value greater than 1 for zeta and you take the square root, it's okay. It will not be resulting to a imaginary value. But the formula now will also change because it became minus rather than plus. So this will be s plus zeta omega n minus, again here we can factor out zeta, then all over you multiply it again with the square root of zeta squared minus 1. Then here we have zeta multiplied by this, or omega n, rather, omega n multiplied with the square root of zeta squared minus 1 all over s plus zeta omega n squared minus omega n squared times zeta squared minus 1. So we can now apply again our formula, but this time it's minus. So if it's minus, what happens to the table? So what's the inverse Laplace of s over s squared minus omega squared? This will be, the inverse Laplace of this will be equal to a hyperbolic function. This will become hyperbolic. So this is cosine hyperbolic omega t. The same true as the second term, yung sine, it's also will become sine hyperbolic because it's minus. So if we take now the inverse Laplace of this whole system to determine y's of t, so we will have 1 over s is this one. Then this one, s plus, we still have e raised to negative zeta omega n t. Then you multiply this with cosine hyperbolic instead of this cosine. Why? Because it's minus. Cosine hyperbolic of omega n times the square root of zeta squared minus 1 t. Then for the last one, minus e raised to negative, or we copy this, zeta all over the square root of zeta squared minus 1. Multiply it with e raised to negative zeta omega n t times sine hyperbolic of omega n square root omega n squared of zeta squared minus 1 t. And we can still substitute our omega d. We can make it just equal to the square root of zeta squared minus 1 in this one. So that we will have 1 minus, we can factor out e, omega n t, multiplied by cosine hyperbolic of omega d t, then plus, again, we can make this zeta omega n over omega d. It's like the underdamped. Then multiply it with sine hyperbolic omega d t. So this is now the unit step response, but this is only true if the system is an overdamped system. This is for overdamped system. What is overdamped system? When zeta is greater than 1. So we have underdamped, less than 1. This is the response. And for overdamped, this is the response. How about for a critically damped system? When we say critically damped, this is when zeta is exactly equal to 1. So what will happen if zeta is exactly equal to 1? So if we go back here, the square root of 1 minus zeta squared will become 0. So this will become 0. So what will happen to the final value? So if that is 0, omega d will become 0. So omega d will become 0. Then cosine, this will be cosine of what? Cosine of 0. And this will be sine of 0. So what is cosine of 0? What is sine of 0? So the final for critically damped system, the response becomes y is t equals 1 minus e raised to negative zeta omega n t. This will become 1. Then the other one will become sine hyperbolic of 0. So this will become plus this omega d times t. So there's no sine and cosine in the system. This means that this is the fastest response without overshoot. So the critically damped, or zeta, when zeta is equal to 1, is the fastest response to reach the final value without overshoot. So if you further increase the speed, you just need to decrease zeta, but when you decrease zeta, it will become underdamped. So if you increase zeta, it will be greater than 1, then it will become greater than 1 will become overdamped. And what happens if zeta will be equal to 0? What happens if zeta is exactly equal to 0? And this will become, if you look at here, if zeta is equal to 0, so what will happen? The exponential term will be e raised to 0, it will become 1. So if it becomes 1, so let's go back here, this one. If this becomes 1, what happened? It will become just cosine or sine functions. So what does this mean? This means that the function will not oscillate, but it will sustain the oscillation. So this will be a sustained oscillation. So it will be a sinusoidal. It will never be stable. So this is unstable system oscillation. Sustained oscillation. So it will never be stable because it's just oscillating all throughout. So to picture these different factors here, let's try to plot that one, the one that we derived. So let's use desmos. This is used to plot some functions. So let's say we have y is equal to our time domain, where we can make it as our x-axis. So we can plot first the first one, here under dump. So we have 1 minus e raised to negative zeta omega n t and so on. This will be square root of omega or omega n times the square root of 1 minus zeta squared. So we can make omega n and zeta our variable in this one. So we have 1 minus e. Then this will be raised to negative, let's say our zeta is a. Then we have our omega. So omega here, omega n, let's call it b. So you just multiply it by b. Then let's make a slider so that we can adjust it later on. Then you multiply it with x for our t domain, t variable. Then you multiply this with Uh, the next one. Here we have cosine omega dt times this one. So cosine of omega d, and that's just equal to omega n. Our omega n is b. We multiply it with the square root of 1 minus omega, or minus zeta, or zeta is a squared. A squared. Then you multiply this with t, or x. Then plus, we need to add the other term, zeta times omega n omega d, or we can directly use this one, zeta over the square root of 1 minus zeta squared. Zeta, so plus, zeta is a divided by the square root of 1 minus a squared, 1 minus zeta squared. Then you multiply this with, we have your sine omega n times the square root. Sine of omega n, or omega n is b times the square root of 1 minus our zeta is a squared. So this omega d times x. Then let's review this. 1 minus, so we can put here quantity to make sure this is inside that cosine. Okay, that's okay. And we can plot now. So we can increase the values for A, B. So A, remember our A is the zeta, or the damping ratio. So when A is equal to 1, this is critically damped. So we cannot use that equation here. It's only possible if A is less than 1. So we can set values for A. We can start at 0 up to, let's say, 2 with the step of 0.01. So we can adjust now this one, because this is under dump, should be less than 1. So if you look at our plot, so if it's equal to 1, so let's start again with 1. We don't have 1 or greater than 1, because this is only possible for less than 1. So we start at 1. So here, we only care about the positive values here. So we can increase the frequency. This one is the frequency. So if we decrease the value for A, or the zeta, so we can decrease it. Then if you look at the plot, now we have one overshoot. So let's try to plot our input, y equals 1. So that will be our input, y equals 1 here. Let's change the color of this one. I don't like violet. Let's put it green, or red, or no, blue. So that we can determine the difference now. So if we decrease 0.5, so we have now overshoot here. Our final value is 1. Then if we decrease further our damping ratio, so we start to have more oscillation. until what happens when we reach 0. So when we reach 0, it becomes a sinusoidal. It's unstable now. So it's a sustained oscillation all throughout. It will never be stable. So a good value for a zeta, maybe this one from 0.3 here up to 0.8 something if you want an overshoot. So when we are designing, we can adjust this value, zeta here, because we know zeta, it depends on your system. If you're given a transfer function, we can determine the variables of our system. By adjusting the variables, we can adjust zeta. We can adjust the different specifications of your system. So that will be our next topic. Then we can also plot if it's greater than, what will happen if it's greater than 1. Just copy this one. Then I'll just change this one here. Instead of 1 minus a squared, it will be a squared minus 1. So let's change all of them. So this also be a squared minus 1. Here, it should be minus 1. We remove the 1 minus. What else? One minus. Okay, so let's make it black. So the color of our function will change to black when we are in, if the damping ratio is greater than 1. So let's try to increase this to greater than 1. So that is the black one. Now it became black. Why? Because it means that we are now in this equation here at the bottom. This is an overdamped system because it's now already greater than 1. So if we increase further, oh wait, there's something. Okay. This should be hyperbolic now. So h. I forgot to put the hyperbolic function. H. Okay, that's it. So when our damping ratio is 2, then if we decrease that up to, so the fastest will be 1 because it's the critically damped. But if it's 1, what will happen? Our plot will disappear again. Why? Because it does not meet the criteria for the red one. The first one less than 1 and the other one it's greater than 1. So we need another one. For the critically damped, this will be the new equation. Y of t equals 1 minus, so this should be y equals 1 minus e raised to negative a b x, then you multiply this with what? You multiply it with 1 plus omega d times t. So 1 plus omega d. What is omega d? Omega d is the square root of zeta squared minus, this should not be omega d because omega d squared of zeta squared minus 1, it will become 0. So this should be omega n instead of omega d. So let's correct that. So let's put it here. This should be omega n. So omega n is b. You multiply this with t or x. Then let's change the color to orange. So when it exactly equal to 1, now we have here critically damped. This is now the the time response when zeta is exactly equal to 1. So if we increase, it will become blank. We need to put, wait, because this is a b1 plus bx. It also changes with respect to changing a. That's fine. So we just need to look at the red, and if it's greater than, it's the black. So it's only true, the yellow will only be true when a is equal to 1 or critically damped. So that is the time response of the different or the second order system here. So we have under dump, over dump, critically dump. Now, for our next discussion, we will be discussing the different specifications, and we will be using this time response that we derive to determine the equations or formulas for the different specification. We can use graphing tools to determine them, but we also need to use the formula. Without using the graphing tools, we still need to derive the formulas so that you can still solve them without graphing tools. Okay?